Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's a great pleasure today to introduce Lingjia Tang from the University of Virginia. Lingjia is getting her PhD, finishing her PhD, and she's been working in the area of improving the performance of data center or warehouse scale computers. She recently won an award, the CGO Best Paper Award, and her work has been recognized by Google. She's worked closely with Google in a number of internships. So it's a great pleasure. Thank you.
All right, thanks. I don't know if this is working. Thanks. So my name is Lingjia. Thanks for the introduction. To make it easier for you guys to pronounce it, it's pronounced as Ninja, but with the Ling, with the L. So today I'll be talking about mitigating memory resource contention on the commodity multi-core machines to improve efficiency in the modern warehouse scale computers. So I also want to share some of the insights and some of the discussion and discuss with you guys about when you rethink the role of compiler and runtime system in this kind of emerging computing domain. So let me just first give a little bit background. I'm sure you guys, a lot of you guys are really familiar with this warehouse scale data center, the sort of the computing domain that my work is focused on. So in the last couple of years, especially in the last couple of years, the mega scale data centers have gained tremendous momentum as emerged as a very important computing domain. Companies such as Microsoft, including Microsoft and Google, Facebook, are constructing those mega-scale data centers that host large-scale internet services, such as web search and mail, as I've shown here. And a lot of people really are very familiar with this kind of applications, and some people are really addicted with it. As The Economist magazine points out, that data centers have become very vital for the functioning of the society nowadays. Those kind of data centers are very expensive to build, construct, and to operate. So typically, each of the data center may cost you hundreds of millions of dollars. And the cost and the size of those data centers have grown rapidly in the last few years. So back to a few years ago, we were talking about this kind of data center. We would say, oh, it's a football field-sized building housing tens of thousands of machines. And a few years later now, we're talking about those buildings as tens of football field size. And we were talking about hundreds of millions of dollars. In the recent data center, this one shown, I found this picture on the internet, is Apple's new data center that's actually costing $1 billion. Right? So those things are growing really, really expensive nowadays. And of course, when people spend $1 billion building data centers, and they want it to be very efficient. So efficiency is really critical for the cost. So my work mostly focuses on the memory resource contention on the commodity multi-core architecture, and which is very significant limiting factor for the efficiency in the warehouse scale computers. And I'm going to explain why. So those are the server racks that populate the data centers. And if you look at the machines we use in those kind of data centers, we typically use commodity multi-core machines. So on those kind of machines, we have multiple processing cores share part of the memory subsystem, right? So each core here has its private L1 cache, but they share L2 cache, memory controller, and bus bandwidth to the memory. So if you have multiple applications running on this kind of architectures, or multiple application threads, they may contend for some of the memory resource. For example, one application thread could evict the data of another application thread out of the shared cache, right? Causing significant performance degradation. So in addition to significant performance degradation, this memory resource contention on this kind of multi-core machines also limits server utilization. And I'm going to explain why in just the next couple of slides, but I want to point out here that 1% improvement either in terms of application performance or utilization in a massive scale of data center translates to millions of dollars potentially saved. So it's really important. All right, so let me further illustrate the impact of memory resource contention on both performance and utilization. So here's a really simplified model we have two applications, and we have two options of how we run those applications, right? First, we could actually say each application gets its own dedicated server, as shown here. So we have two machines running two applications. Each application may or may not occupy all the processing costs of this machine. So you have low utilization of those machines, but you get peak performance. The other solutions say let's allow co-location, so we improve the utilization of the server, but we reduce the number of machines we need, but we actually potentially have significant performance degradation because of the memory resource contention. Right? So things get a little trickier when you have latency-sensitive applications, such as web search or mail. Those are applications that are user-facing. You care about its latency. You care about users' experience a lot, so you don't want to actually sacrifice a lot of the quality of service or performance of those applications. Right? So you care about those, and their potential low priority application in this data center, such as batch applications that you don't care that much about, but we do really care about latency-sensitive application. So if those applications cannot really deliver the acceptable QoS, when we actually co-locate those applications with other applications, then we don't want to do this kind of co-location, right? So co-location is often disallowed for latency-sensitive application. So a typical approach is we choose to actually disallow co-location and have sacrifice utilization for performance. So just to show you, the low utilization is pretty common, and it's actually one of the big challenge for data centers. Here's a graph from HP data center, production data center. So one of the key feature of this graph that the observation you can see from this graph is we're spending 60% of the time, or even more than 60% of time running at 10% of server utilization. So this is quite low. Google has a slightly better data. So the official data is around 30% of utilization. I was talking to the IBM fellow, and they were saying the IBM data center, production data center, x86, around 8 to 12% average utilization. So those are really low number. So why is low utilization expensive? If you look at the total cost of ownership of a data center, purchasing server is a huge chunk of this cost. And then on top of that, constructing data centers is a big chunk too. And then the power, right? So if you actually have low utilization meaning given same amount of work, you want more machines to run those work, you want a bigger data center, so those are very costly. So you want to improve utilization in the data center. So therefore, mitigating contention is really critical for improving both performance. Go ahead.
Go back one slide. I just want to understand the pie chart a little bit better.
Okay.
Would it be fair to say that the server cost is a recurring cost? Because servers keep failing, and then you keep buying more and more servers. Whereas the other stuff, not excluding the power, like the data center, that's basically a fixed cost.
Oh, this is actually total cost of ownership annual breakdown. So assuming you have the server for 4 or 5 years, and then you amortize the cost. All right, so the big picture of the work that I'm going to present here, my dissertation work, first we want to understand the interaction between the data center applications and the underlying memory subsystem. And on top of that, based on understanding and insights, we want to actually manage resource sharing between application threads so we can improve the application performance. Also, we want to manipulate the application characteristics so we can actually facilitate more co-location and work consolidation on those kind of servers to improve utilization. So some of the results I have the publication in those domains. So I'm going to briefly talk about those two, and then focus most of the work on this part of the work. I also have other work related to the data center, how we improve data center efficiency in data center. Tomorrow, Jason's going to talk a lot about those very interesting work. You're going to hear a lot from him. So the outline of the talk, I've discussed the motivation and the goal of the work. So I'm going to talk a little bit of the characterization of those applications and how they interact with memory subsystem first. So let's take a deeper look at the memory resource sharing for those kind of architectures. So this is an Intel Xeon Clovertown. This is actually widely deployed in Google production data center. So on this kind of machine, we have 2 sockets, and each socket will have 4 processing cores. And 2 cores are sharing a last level cache, 4 cores on this socket are sharing a bus, and then 2 sockets are sharing a memory controller. So you have 3 major components of sharing on this kind of architecture. it's one interesting to notice is the sharing could potentially have a constructive or a destructive performance impact. If threads actually belong to the same application and they share data and it fits nicely to the shared cache, then you basically prefetch for each other and you are reducing the coherence traffic and the bandwidth traffic. So it's a good thing. But potentially they will also contend for those resources. When that happens, it's a destructive kind of a performance impact for those applications. Another interesting thing is the thread-to-call mapping determines which resources are shared among multiple threads. In this simple example, those two threads are sharing those three resources. So if I move the thread to another call, I'm only sharing memory bus and memory controller. If I move the thread to another socket, we're only sharing memory controller here. So it's a really interesting feature of those kind of architecture. So the research question of this part of the talk is, what's the performance impact of those thread-to-call mapping and the memory resource sharing for the application performance, for emerging large-scale performance that we care about, data center performance. So some of the prior work, people have been using spec, and they conclude there's significant performance degradation due to memory resource contention. And there's a lot of work in the hardware community based on. But there's a recent work in PPOP 2010 that concludes that cache sharing does not matter for the contemporary multi-thread applications. So our question is, what about the large-scale emerging data center that we care about? What about the performance impact for those applications? So let me show you some of the key results that we found. There's more results and details of those applications in my publication, so we could talk offline. So this is intra-application sharing, meaning we're interested in finding out the sharing among threads that belong to the same application. So here are the three large-scale applications we use, including web search and bigtable. Content analyzer is a semantic analyzer. So in each case, in each application, we run it on the previous, we show the Clovertown machines in three different configurations, sharing configuration. So from the left to right, you can actually think it as more and more sharing among threads that belong to the same application. So the y-axis is the normalized performance. So one thing to notice here is there's a big performance swing up to 22% for those applications, for example. Semantic analyzer degrade from more sharing, indicating there's contention among threads. The performance suffers from the contention, and web search as well. So, but there's also an interesting thing to see from this graph that it's both constructive and destructive impact, right? Because if you look at content analyzer and web search, they're degrading from cache contention, bandwidth contention, but bigtable actually benefits a lot from the cache sharing. Go ahead.
So just to make sure I understand, so you care about single machine performance, ignoring potential contention on the network?
Yeah, this is really just single machine microarchitecture resource contention. So we're not looking at network contention. And for example, the web search, we're looking at leaf node performance. So
this is sort of a request comes in, it's completely executed on that machine.
Yeah.
It doesn't make any remote calls, nothing,
yeah.
and just...
Yeah. So basically, we use queries of real-world queries, a trace of real-world queries, then we actually fed these queries to this machine. So the leaf node.
But do you have a sense of how much this impact actually translates to the end-to-end latency, which is what the user sees?
I don't know. I don't have an exact number of how it translates to real in a complete latency. I think for web search latency on the real machine, on the backend machine, does not. It's not going to be the major dominant part for the latency for web search, because the network latency is so big that your query latency in a single server might not really matter that much. But the key for the backend is you really want to improve performance to actually reduce cost, right? So it's not so much about performance; it's a lot about cost. But we do care about the latency of those queries on those machines. You definitely want the best machines for those queries, best performance for those queries on those machines. All right, so there's a constructive and destructive impact for both for three applications, and then we look at inter-application sharing. So basically, what's the impact of sharing among applications? So if you, in this case, where we actually co-locate another application with multiple threads onto the same architecture, what's the performance impact? So here are the results. Each graph is is a single application content analyzer, 3 different kind of running scenarios. Running alone, you've seen it already. Running with another stitcher is image processing for Street View and another benchmark. So you could see that there's performance degradation from contention because the performance basically dropped from running alone to running with other applications. Another really interesting about this graph that I want to point out is the optimal thread-to-call mapping actually changes when the co-runner changes, right? So if you think about content analyzer, when it's running alone, its best performance is running actually spread its threads across the 2 sockets. But running with stitcher makes it actually benefit from cluster all its threads together. And similar for web search, it changes in different settings. And in this case, it's preferred to actually share cache with its own threads, but not share bandwidth with its own threads. Big table always benefit from the sharing. And it's also interesting to notice that this difference between thread-to-call mapping performance could be pretty significant. It's up to 40% for big table in this case. Right, so a quick summary. I have a lot of more data about this kind of study in the publication that I don't have time to actually show here, but I want to highlight some of the things we found. Contrary to the prior work, we found that the memory resource sharing actually really matters a lot for large-scale data center applications, and the performance swings up to 40% simply based on different thread-to-call mapping. And the interesting thing is optimal mapping changes when the application changes, when the co-runner changes, when the architecture changes. And I highlight those two is because basically what they're saying is there is up to 40% performance opportunity that we left on the table without thinking about thread-to-call mapping, right? Without thinking about this interaction between the application and the microarchitecture. And so it really, the next question we ask is, how do we achieve the optimal thread-to-call mapping?
I have a question. All these applications that you have mentioned, do they involve any synchronization, any locking?
Yes, but not so much. There's, of course, synchronization in those kind of applications, but it's not a huge amount of synchronization-bounded applications. And that would be really interesting to see, lock contention, that kind of performance impact on those applications. But we're only focusing on memory resource contention on those applications.
So, you say that these are sort of large-scale data center applications, but then you look at a single box performance, right? So, what is really different about these applications than some other applications that would not run at large scale in a data center? Is it the workloads are different, the memory access patterns are different that really makes this now interesting compared to non-data center applications?
There's actually a publication that coming out of Microsoft actually really, there's multiple publications comparing those workloads with spec in terms of, different, how they access a different kind of functional units or the IPC difference and memory access different patterns difference. And I think you will find there's quite a difference between those applications, between spec. And there's new work coming out thinking about how to use this different characteristics to actually design new servers architectures. That's not really, for example, instruction cache is really important for those kind of applications, which is kind of different for spec. So there's a lot of difference. But we could talk offline about it. So how do we achieve this optimal thread-to-call mapping for better performance? So I'm going to just talk really briefly about this section. So we basically manage the resource sharing by doing intelligent thread-to-call mapping of those applications on this architecture to improve performance. So there are 2 approaches that we present in the paper. One is a heuristic-based approach, and the other is adaptive approach. And so the heuristic-based approach, the key idea is that's actually figure out the application's characteristics and map the threads according to the application's characteristics and the machine memory topology. So what kind of cache sharing this machine actually has, for example. And we identify 3 important application characteristics, including the amount of data sharing among threads in this application, how much cache usage and bandwidth usage.
I have a question.
Yeah.
But I thought you just said that this thing depends on the co-runner. So how can you make this decision in isolation?
Yeah, that's a good question. I'm going to get to it in a... So the heuristic-based approach is basically saying, let's say you have an application and you have a co-runner. The key idea is to say, compare the potential contention within the application versus the contention between the application, and then you choose the best thread-to-call mapping and minimize this contention. Right, so because if you actually have a lot of data sharing, then you potentially prefer just share data with your own threads instead of sharing cache with other applications, right? And if you have a lot of contention among its own thread, let's say you have another application coming with less contention, then you potentially want to share cache with another application. So this is how we actually decide a mapping. So you need to know the application characteristic of all co-runners, and you need to know the memory topology. So again, okay.
Fixed for co-runner, right? So you pick a co-runner already.
So this is fixed for architecture. But depends on the co-runner, you may go different paths of deciding how to map.
Right. So you know the co-runner already. You are not choosing a co-runner.
That's a good question. Yeah, we're not choosing co-runner. That's a different research question. We basically know that we need to actually manage those two for multiple applications. Then we decide how do we actually thread.
Can I ask another question? Sorry.
Sure,
for so
go
many
ahead.
questions. So in these warehouse scale computing scenarios, is the set of coroners more or less static and remains unchanged over a long period, or it changes very fast?
They're really long-running applications. So when you actually, once you decide the co-running situations, they potentially won't change for days, but they will actually change. Right? So if your program crashed, for example, so the job mapper with new task coming in will decide where the task is. So they use basically a bin packing algorithm, and they decide where to actually map those applications to the machine. In that case, you actually have co-runner changes. But once it's running, it's going to run for a while. So, and this is to address your question. It's architecture specific and potentially change with the co-runner, and we require profiling. So this is not, this is doable, but it's not necessarily optimal. So we propose the adaptive TTC mapping. And the insight is, because the optimal mapping changes based on a lot of things changes, co-runner changes, architecture changes, so why do we just do it online? So the key idea is we have the competition heuristic, we have the learning phase that we actually basically go through the search space in a smart way. And then we pick the best thread-to-call mapping, and then we execute it for a while. So we basically loop this. And then to address your the question about data center application, they're long running and they have very steady phases in general. But they may change co-runners and different tasks. The same binary could be potentially mapped to different architectures. Right? So this kind of approach is more dynamic, addressing those kind of changes in environment. So some of the evaluation for the adaptive mapping, those are both on real application on real hardware. Those are hardware, so in production hardware. And the performance is on the y-axis. The x-axis is the workload. The blue bar is the average random mapping. So the green is adaptive, and the yellow is the optimal mapping you could do for those kind of workloads. And the baseline is the worst case mapping. So basically, this is definitely better, significantly better than worst case. Worst case is not, you don't want to do worst case, basically. And we're really close to the optimal. And we're beating random mapping. So on both architectures.
So did you do, I mean, are those bars significant? Do you do multiple runs here? There's probably variability, right, between every run.
Yeah, so the benchmark here, so we benchmarkized our application. So we basically make sure it's always repetitively run the same kind of the trace that we're using. And then the benchmark round between runs is 1% difference. So
what about the changes in the workload? So say the binary is the same, but then depending on what the requests are coming in, it might change.
Right, so to address that, we basically use really long traces for queries. So it's basically, it's kind of averaged out. So we're looking at the average performance of those queries. All right, section summary. We present the adaptive mapping threads to actually improve the performance for those applications. And I want to highlight the importance of taking advantage of the interaction between applications, among applications, and between applications in the microarchitecture. And I think this is where a lot of runtime system will come in to actually improve the performance for those kind of emerging domain. So I talked a little bit about improving performance. I want to switch gear a little bit and talk about server utilization. So how do we actually improve server utilization? So when you think about improving performance, we manage application level. So application level manage how they actually share resource, share the common memory resource on the multi-core architectures. For improving server utilization, the goal is to can we actually manipulate applications characteristics using compilation technique or other techniques to improve to reduce the memory contention and improve the server utilization. So here we present the compilation technique to manipulate application characteristics so it can facilitate more workload consolidation on those kind of machines. So here's, I've showed this graph before, but basically I want to highlight the goal of this work. So again, the option 1 is to actually say disallow co-location, so each application is running on this single dedicated server. So you have idle costs for each server, you have really good performance, but low utilization. The other option is saying we co-locate those applications, but we potentially have really significant performance degradation because of the memory resource contention. And for latency-sensitive application, we don't do this because we want to actually deliver the acceptable quality of service. So the goal of this is to say, let's mitigate the contention the low priority application generates to the high priority application. So the high priority application, the latency sensitive application can deliver the acceptable quality of service. So when we do this, we could facilitate more safe co-location, meaning the co-location, when we do this, the high priority application delivers satisfactory QoS performance. And this, we could actually improve utilization, even if we actually sacrifice a little bit of the even if we sacrifice a little bit low priority applications performance, we still gain this kind of utilization, right? Because if you compare this graph to this graph, those part of the idle costs are previously idle, and then we actually basically extract the utilization from that part of the architecture. So that's the goal of this part of a work for improving server utilization. So a lot of research questions that come with how do we do this? How can we actually mitigate the contention by changing the application's characteristics? So we want to make the low priority application less contentious. So how do we do this? How do we actually identify? Can we identify the code regions of the low priority application that are really contentious? And how do we actually change the characteristics? So compiling for niceness is our approach. It's the first compilation approach to address this kind of challenges for multiple core running applications in this kind of domain. So the highlight of this technique, we pinpoint the contentious code regions. Then we actually apply novel compilation techniques to manipulate its contentious characteristics. So reduce the contention this low priority application may generate when it's co-running with other applications. So we could actually allow it to actually co-run with high priority applications. So some of the key insights, before I go into the details of this work, traditionally when people think about compiler, they think about we're compiling an application, it's going to be the single application, and we're running on this architecture. And so we're focusing on performance a lot. But in this kind of new domain, when you have a lot of workloads, you want to consolidate those workloads on the server, and the number of cores on those servers is growing with every generation. So you have a big pressure, and we can't really overlook this trend of we want to actually consolidate workloads in this domain. In this kind of a domain, there are more objectives you may need to think about when you think about compiler, right? How aggressive application could really aggressively use memory resource and actually get the performance, but is it really the best way to do it? What about the influence this application has to the old co-running applications for the...
Traditionally, you can imagine having OS priorities,
yeah.
Right? And just scheduling things, scheduling the one that shouldn't contend at a lower priority. Why is that not a good solution in this space?
Well, so OS has its... Well, I would say mostly because you want to change the application's characteristic of the low priority application, and OS is not really tasked with doing that. And here it's not really a time sharing kind of a situation where traditionally when you think about OS, you would think about NICE being application time sharing a resource. So you can actually tone down the priority of one application potentially and actually do the time sharing. But here, two applications are all co-running at the same time. They're always running simultaneously, right? And also, a lot of challenge comes with how to do this for OS, but I'm going to talk about it a little bit more when I go.
So a follow-up question. For triggered by your response. So is it true that they don't do time sharing at all on an individual core in this warehouse scale computing scenarios?
There's definitely some kind of amount of time sharing, but not so much. Because if you actually have your threads or your application less than the actually available cost, then you don't have to do time sharing for a lot of situations.
It looks like the niceness is a matter of billing for the true costs of an externality imposed by an application. If you did data center billing, how would you bill to get niceness into the mix? Just like you bill for megabytes of memory and for seconds of computer time.
Right. This work mostly looking at the data center that provides internet services, right? So you basically have control of those applications. So
you
now,
bill yourself, so.
Yeah, you build yourself. So it's easy to negotiate and say which application or which application has higher priority, right? And we often do this in the data center. But I mean, I can imagine if you do this. This may be a wild claim that I haven't really looked into it, but if you do this, you could actually say select my priority with different billing price, right? I have batch application. You could charge me really cheaply, just get it done, whatever. So those kind of options.
Can I have one more question, kind of on the basic assumptions? So a lot of the data centers seem to assume that you only one job per CPU. Mm-hmm. So what are they doing when they're overloaded, when there's more than one job per CPU that needs to be done? Do they not do time sharing? Do they hold it up at the queue until somebody's finished?
My experience is they often do time sharing at this point, and then your performance is going to degrade a lot. And then the operator is going to have to come in and say, we can't do this. Yeah.
So then shouldn't the queue that's sending them to
yeah, they do bin packing algorithm. So they basically, application will come with the sort of resource requirements saying how many megabyte I want, how many CPU time I want. And then the mapper, the job mapper, the cluster scheduler basically decides how to actually map those applications. If the machine still has available resources, then I'm going to map this job. Then yeah.
So it seems to me that a lot of that decade-long research in OS, all the topics that they used to make such a fuss about, they are just irrelevant in warehouse scale computing. Is that correct?
Is it OS? I mean, I think OS people really need to rethink about in this kind of domain what kind of priorities and.
The optimization criteria was not quality of service on a single job. That it's fairness. Yeah. And so the operating systems community optimized for an important part of the space. And that is a different, now it's how fast you get the answer back or someone's not going to click on your website.
Yeah. Thanks. So another insight is, in this kind of domain, when you sacrifice a little bit for performance of low priority applications, you could facilitate safe co-location and win a lot of utilization in the end. So in other terms, when you sacrifice a little bit of your self-interest and performance, you win big in the big picture. And that's a life lesson. Being nice is sometimes good for the big picture. And also, in this kind of data centers, we know the applications that we're running, they're long running, and then we have the source code available. So we call our system QoS-Compile, and here's a review of the system that we have a profiler that basically identifies the contentious region of those low priority applications. And we also have a compiler that target those those contentious regions, and when we compile those regions to mitigate the contention nature. So I'm going to talk a little bit of the the profiler first. So this profiler is based on hardware performance counters because they're fairly low overhead. The idea is based on how aggressive those applications is using a certain memory resource, we actually predict how contentious it may be when it's running with other applications. So the applications running the profiler based on the performance counters will actually predict a contention score of the execution phase. So we identify the execution phase that with high contention score, and then find the associated code regions that have the high contention score. And there's a lot of thinking and work that goes into how to actually build this kind of prediction model, and we use a regression, and here's our model. And I'd like to talk more offline if you're interested. But let's take a look at the performance of this model. Here are the two prior work. Those are the work that published at S+. That using last level cache miss rate and reference rate to actually predict how contentious the application is. And this is our model. So as you can see, we have a much better linear regression, linear coefficient correlation. And
is that taken from your interferences between the different jobs, or what are the inputs to your model?
Right. So the input to the model is the performance counters. For example, last level cache licensing of the application, L2 licensing. There's a lot of reasoning of why we actually select certain performance counters. The output is contention score, right? So basically, imagine you have certain licensing when application runs, then we actually calculate score. Then we compare the score with the average degradation this application when running cost to the co-runners.
Okay, so you're actually predicting something different as well as using multiple inputs to help you predict it, right?
Yeah.
Okay.
But so is this on a per region basis? I'm not sure I understand what the timeline is.
Oh, sorry. This is actually application level.
At the entire
So average application,
Okay.
average cache miss rate, for example, for the entire
And how do you do it by region? How do you identify contentious regions?
I have a graph that I'm not sure if I have this in the backup slides. But so basically, when it's running, we every milliseconds sample the performance counter. So you basically get every milliseconds get a contention score, right? And then by region, we did instrumentation to actually identify. So we're basically just looking for the execution phase that corresponds to that part, the code region that corresponds to that part of execution phase, which is not.
So you do a phase analysis as part of this then?
Well, we did ping. We used ping to actually. So the way we did it is basically, so we do two pass kind of analysis. One pass, we basically get the contention score of the execution phase. We also record the instruction executed during that phase. And then the next phase, the next pass, we so basically you got the contention score every 1 millisecond, and the instructions executed every 1 millisecond. The second pass, we did a ping instrumentation, so basically counting the instructions executed, and then identify the code regions that are executing the mapping instructions of the first phase, and identify the code regions. So I think we have more details in the paper, but we could talk more offline if you. Right. So there's also a phase graph that will show the phase. We actually do a pretty good job identifying the phases. So that's the compiler. That's the profiler. Let's take a look at the compiler. So the intuition behind the compiler is we use rate reduction to actually reduce the contentious nature of a contentious region. So we basically reduce the memory request rate of those regions. And here's some illustrative example to show the intuition behind when you reduce the memory request rate, you reduce the contentious nature of the application. So if you have two applications running, application A and B, and let's assume some certain initial last level cache content and access order, you will have execution time for B, for example. So when you actually slow down A's access, basically what you changed is the access order here, that you prioritize B's execution, the memory request, right? Because A is actually slowed down, so B memory requests get prioritized. And that will actually have a big impact on the performance of B. So in this illustrative example, B's execution is greatly reduced. So based on this intuition, we have two techniques to actually reduce the memory request rate. One is padding. Basically, we insert no ops into those code regions. So the idea is that the application execute a few instructions and then executing no ops. So during this phase, no memory request issued. Another one is naps insertion. So basically inserting nap. So you basically can control, let the application run certain milliseconds, for example, and then let it sleep for a few milliseconds. To use those techniques to control the rate reduction. And you may wonder that those two techniques are really similar, right? Because they're just basically let application to execute for a while and let it sleep for a while, or inserting no ops for a while, that they should have the same kind of performance. But in experiments, we found out that might not really necessarily always be the case. So here is some performance showing padding and nap insertion in action. Y-axis here is the quality of service of high priority application. The x-axis is the execution rate of the low priority application. So from 1x to 0.4x, we slow down this application by inserting no ops or padding or napping. As we slow down this application, you can see the performance, the QoS of the high priority application improves. Right? And there's 3 lines of napping with 1 millisecond every nap, or 10 millisecond, and padding. So in this case, we actually have really similar performance for 3 techniques. In this case, however, we could see that nap every 10 milliseconds actually outperforms all the other 2 greatly. So even if you slow down the application, one application to the same execution rate, but different techniques, you may have a different effect in terms of improving the QoS. So same rate reduction may not really have the same effect. And so it turns out this performance difference is because of the granularity when you do the rate reduction. So let me illustrate this one. So if you think about a performance of a high priority application, let's say it's actually starting in the performance really low because of the other applications generating interference. And the nap and padding starts here. We start to actually slow down the higher low priority application. In this case, high priority applications performance only picks up, instead of just, jumping up to the really optimal performance, it only picks up. That's because when you just start napping and padding, there are still memory requests that are coming from the low priority applications still getting served in the system. So it takes a while to actually cool down those memory requests. It also takes a while to warm up the cache for the high priority application for it to pick up the performance, right? So what this really says is actually when you slow down the application, the granularity you pick to do this actually matters. So smaller, fine granularity for padding, which is in terms of cycles, may not really give you the best win for the slowdown you actually sacrifice. Also, comparing padding and napping, napping is easier to do a more accurate timing control because you could potentially have a timer, and it's more power efficient because we're not really executing no ops in this case. All right, so some of the evaluation for QoS-Compile, and this is combining both identify code regions and apply the code transformation to those applications. Here on the x-axis, we have the high priority application. Y-axis is the quality of service of the high priority applications. Each bar, the first bar is when those applications running with the original LBM with no padding, the original one, basically no QoS-Compile. And the yellow bar is when we actually identify the code regions and inserting naps into those code regions. And this is every 10 milliseconds, napping for 10 milliseconds. The purple is every 10 milliseconds, 20 milliseconds. As you can see here, we actually greatly improved the performance of those high priority applications up to 85% and 90% of its original peak performance. Similar results, and there are more results in the paper. And let's take a look at the utilization when gain. So basically, those are the application, the low priority application, when it's running with those high priority application, because we slow down, so we're not really running at 100% of the execution rate. But we still gain significant, around 40% in this case, 50% around this case, of the utilization of the cost that previously would be idled if we don't really do this kind of co-location. So we also have really similar results for the Google applications where we actually improved the web search for up to close to 90% in this case. So the summary is we pinpoint these contentious regions and we apply code transformation to those regions to mitigate the contention the low priority application generates to the high priority application. So we could improve server utilization because we facilitate this kind of a workloads consolidation. And I want to actually stress the multi-objective compilers in this kind of era that you're actually looking at a lot of trade-offs more than we actually are very used to think about before. All right, but
so just a quick question. So you're just inserting these no ops. You're sort of stretching out the execution.
Mm-hmm.
have you thought at all about sort of more sophisticated techniques or other things that can be done, maybe with more, like, you know, if you think about a compiler can reason about the code, you know, and figure out, you know, do different instruction scheduling, things like that. Are there other things that could be done that were more sophisticated?
I think it's potentially there's things that could be done. I was looking at, you know, thinking that some of the optimization you could think about, you know, memory hierarchical optimization, the compiler optimization we do to actually optimize for the cache structure and all that, or loop transformation that potentially we change the memory characteristics. But when we look at those kind of optimizations, the performance impact or the impact in terms of mitigating contention is it's quite small comparing to you really slow down the applications. Right? If you think about loop transformation, potentially you're looking at maybe 6%, 8% of performance. Well, for 6% or 8% of performance in terms of changing the high priority applications. If you change the memory characteristic access pattern of your low priority application by loop transformations, the impact it has on the high priority application is really small compared to just really slow down a lot. So I think potentially there are things to be done, but I choose to actually go this route because basically the benefit you're getting from those is not as big. All right, so why be nice if not necessary? So the last part of the work that I want to talk about is a fairly new work that would dynamically regulate the pressure that we have on the memory subsystem. The key idea is compiling for niceness is a static technique, right? So you basically have to be really conservative. You have to throttle down the application without knowing how much the high priority application may suffer from the performance degradation or contention. So why do we do this reactively online? We could dynamically manipulate the application characteristic based on the performance degradation we actually observe and based on the contention that we actually detect, right? So we could avoid unnecessarily slow down. So if the high priority application, for example, is not really suffering from contention, we don't have to slow down the whole low priority application. And we could actually achieve more accurate QoS control because you're actually monitoring the QoS online. All right, so the overview of this technique, we have the compiler that basically is profiling based and identify the contentious region and instrument mockups to actually invoke the runtime system. We also have the runtime system that basically tasked with monitoring the QoS, detecting contention, and feedback control to actually control how much throttling down and how much nice you want this low priority application to be. So the compiler here is really similar to the compiling for niceness. We use the same profiler to actually identify the contentious code regions, but instead of actually inserting no-ops or paddings, we insert a mockup to actually invoke the runtime. Here. And the runtime system is where a lot of the interesting things happen. So we have the monitor that's attached to the high priority application, which can monitor the performance counter information. So it's actually stored in the shared memory in our system, in the circular buffer. And the NAP engine is the part that's actually attached to the low priority application. So the low priority application can invoke runtime of this NAP engine. Basically, this NAP engine will read the monitored information of the high priority application and detect the contention and actually respond according to the contention detected and the QoS of the high priority applications. So I'm going to talk a little bit more of this part because this is actually really interesting. So to detect the contention and react to this contention, we could have potentially implemented different kind of policies. So in this work, the first policy we tried is let's do a simple way. Let's just conservatively throttle down whenever the high priority application suffers QoS degradation, right? So it could be false positive, but let's just do it really conservatively because the QoS degradation may not really just be simply due to contention. Another way is let's do it feedback controlled. So we have different states. We execute for a while. Then we actually go to the check state to actually see whether napping or our technique will potentially have impact on the QoS. If it does, then we actually continue to nap. If it doesn't, which means maybe there's QoS degradation, but that's not necessarily caused by contention because our technique is not going to be able to reduce this contention or improve this QoS. So it's not necessarily caused by contention. So that's actually just let the low priority application execute. So let's take a look at those two techniques in action. So here, this is Sphinx running with, which is a spec benchmark, running with a low priority application. And the red, this is the ref input, and the x-axis is the time, and the y-axis is the normalized IPC. So if it's 1, meaning there's no contention, it's running peak performance. So here you say the QoS when Sphinx is co-located with the original low priority application. And the blue bar is when we actually apply the reactive niceness here using simple to the low priority application. So you can see the IPC improvement here. Similarly, here we have the red bar, the red line is a similar line, which is the original performance. And here is the green line is when the targeted reactive niceness is applied to the low priority. So the big takeaway point from this graph is you can see this line is very stable. It's around 90%, which is our target QoS. And especially comparing to the simple, they're both effective, but the targeted achieves much more accurate QoS control because it's actually monitoring the feedback. It's monitoring the feedback and effect of throttling down on those applications.
Is QoS defined on just the high priority application, or is it both the high priority and the low priority? Because if it's just the high priority, I could just say, well, I'm not going to even run the low priority one, right? And I've maximized QoS for the high priority.
But then you actually sacrifice utilization.
Sure, but if QoS is what you're trying to optimize, then I guess the question is, what's the objective function, right?
All right,
Does it take into consideration both utilization and quality of service?
I would think the optimization question, if you want to really formally define it, is the constraint is the QoS, that you want QoS to hit certain constraint. With that constraint, you want to maximize the utilization. So that's how I would actually think about this optimization. So for example, the constraint here is we really wanted to actually guarantee 90% of the QoS. And then we could say, with that, give me the maximum performance you could actually give me. But, well, I want to say I think this is a really nice way of thinking about it because you're actually giving people a lot of flexible spectrum of selecting the trade-off between the QoS and utilization, right? You could say, I care about 80%, or give me the maximum utilization here. So people basically have, a knob that they could actually work with in a data center. All right, so let's take a look at another graph showing comparing simple and targeted. So again, the red line is QoS when co-located with original. The blue line here is simple when we apply it to simple, so it's actually fairly stable here. The green line is using targeted. So they have very similar experiments. However, when we look at the nap duration decided by the nap engine of those two heuristics, the green line here is targeted, which is much lower than the simple, meaning we're actually doing much less slowing down to achieve the simple performance. Because nap duration is basically how long you actually slow down you let the application to sleep. So, and this is because target is using a feedback control that basically detects how much of the necessary throttling down you need for the certain performance you want. So again, both are very effective, but target is better for improving utilization than simple.
Do you have utilization numbers for those scenarios?
Oh, so go here. So so this is I think this is every 2 milliseconds we nap. So this is every 2 milliseconds our napping duration. So it's a little over 0.5. So it's 0.5 divided by 2.
Related to the nap time.
Yeah. So let's say every 2 milliseconds you nap. So every 2 milliseconds you run full speed, and then you do a nap. For example, 0.5 milliseconds, then your utilization is 0.5 over 2.5, which is 80%. All right, so let's take a look at the evaluation. This is comparing our reactive niceness to QoS-Compile. Again, two high priority applications running with original low priority and running with the reactive niceness, and this is running with the QoS. And you can see those two performances are really similar. However, when you compare the utilization, we achieve much, much higher than the QoS-Compile. This is because we are dynamically figuring out how much utilization we could get for the performance we desirable performance. And this also is static because you basically, so you only see 2 bars because you basically decide how much you want this application to throttle down before even knowing it doesn't really change when you actually change corunners necessarily unless you actually have to specify. But this one is more dynamic that you could actually, based on what kind of application the low priority application is running with, and throttle down those applications accordingly. All right, so more evaluation, and I'm not necessarily going to go through, but here is to demonstrate that those are the utilization number and those are the QoS target that we hit. We get above 80%, 90%, and we're doing a pretty good job maintaining 90% if that's our target. All right, so some of the performance efficiency number that the red bar is where we actually run 2 applications on the separate machines as disallow co-location, and the green bar is we actually run those applications together and using Reactive-Niceness to control 90% of the QoS. So we achieve 90% of QoS, we have utilization, and we're much more power efficient. All right, so the section summary here, the Reactive-Niceness basically you take advantage of static compilation technique, but also dynamically regulates the memory pressure on those kind of machines to facilitate utilization, co-location, and improve utilization. So conclude, we showed we characterized the impact of memory resource contention on those large-scale internet service applications. It turns out they are actually very, very important. And based on the insights, we showed the thread-to-call mapping technique that improved performance, and also the combining for niceness and reactive niceness to manipulate application characteristics to improve the utilization in the data center. Some of the future work that I'm thinking, so we're also using a lot of managed runtime in the data center that we haven't really looked into how to actually construct managed runtime that's aware of this kind of trade-offs between QoS and utilization, and potentially there could be more flexible research that could be done in the managed runtime space. Again, runtime system infrastructure in the WSC is still quite new and emerging, that there are a lot of interesting things that we could actually look at, particularly take advantage of the interaction between application, among applications, and between application and the microarchitecture. Also, there are a lot of mobile systems that are emerging, the hardware that have been evolving with really fast turnaround generation time for mobile services. And there's a lot of heterogeneity going on in this kind of system that we really need to think about how do we build a software stack and compiler runtime system to really take advantage of those systems that I think would be really interesting to look at. All right, so with that, take questions.
Your last graph had kilo instructions per watt. Should it be per joule? In any case, the number looks low, but I haven't done the numbers.
It's kilo.
Instructions should be per joule, or instructions per second per watt.
I look into it. I don't. Yeah, maybe you're right. I didn't. Well, basically, what we did is using the power meter. Yeah.
The power meter gives you energy on the Sandy Bridge. Doesn't give you power, it gives you energy, even though it's called a power meter.
Yeah.
If you're using the Sandy Bridge one.
Oh, we just basically use the one you could actually plug in for measuring like household appliance kind of thing.
Oh, yeah?
So we actually measure the system performance because we really care about the whole entire system.
Oh, so on the wall, so you're just doing draw out of the wall, not the performance counter?
Yeah, not the performance counter. I've never tried the performance counters. It'd be really interesting to try those performance counters and see. Yeah.
Low priority application does a nap. Is that yielding the CPU? So talking to the operating system?
Mm-hmm. Yeah.
How robust and general are those results? Are you confident that they would basically the general insights that you have drawn from this work apply to data centers? I mean, can you comment on that?
I think it's pretty general. I think I've shown some of the Google applications, and those are the data that we do with Google application on their production machines. So, and I do know that they're really working on this kind of techniques right now. So
So maybe to point out a little bit more on that. So you opened up and talked about low utilization. That was kind of the motivation. And then a lot of the benchmarks, though, were spec, which are just integer codes that don't do any I/O. So I'm curious, do you have any ideas about how much I/O is going to have an impact on some of these things? Because the spec benchmarks are not designed not to have I/O, right?
Right, so the Reactive-Niceness work, we're not using any Google applications because I was not really doing internship when I was actually did this work. But the QoS-Compile was using comparing spec and Google application, and we actually achieved really similar results. That's why we're really confident that we could actually use spec for those kind of applications. In terms of I/O, whether Reactive-Niceness will actually have an effect on I/O, I don't have data, so I can only tell you that. So the reason why I didn't really worry that much about using spec is because a lot of web search view, those kind of applications, their data mostly resides in the main memory. So that you want to reduce as much as the I/O operations for that that kind of application, just because you want higher latency. Higher latency. You don't want higher latency. You want lower latency. So you want everything to be in the memory. But there are certain applications that I/O would be an interesting thing to look at. For example, the Gmail actually has a lot of I/O that. I don't want to really say necessary. I think the main idea may be potentially applicable in those kind of applications, but I don't really have data for